Hi, welcome. We'll start at exactly 7. So let everyone else join and we'll start at exactly 7. 4 minutes. Okay. Am I audible? Can the two of you confirm? Okay, perfect. So yeah, we'll start at 7. So meanwhile, if there are any doubts, you can ask those. And while I wait, I guess I should sketch what we are going to do today. That way we have one more thing. So today we don't have the luxury of extending this class because I have to immediately take another class at 8:30. So let's hope this goes according to schedule. So today we'll be reviewing the necessary number theory for ISI and CMI entrance. By necessary, of course, I mean we'll be going a bit beyond. We'll be more than prepared. That's the idea. And this is one of the longest topics, and unfortunately, we can't extend this class. So let's see. We'll look at some basic divisibility results. So I'll be doing a lot of quickly stating and moving on today. We'll look at the GCD, shows up a lot, and what other topics do we need? We'll look at the Euclidean algorithm to find the GCD. We'll look at Diophantine equations, linear Diophantine equations anyhow. We will look at the fundamental theorem of arithmetic, so FTA. You can thank Gauss for that, like a lot of other things. We'll look at linear congruence. So this will include stuff like your Chinese remainder theorem as well. And what else do we need to look at today? Fermat's little theorem, Wilson's theorem. We will look at the number theoretic functions. Am I forgetting something? Anyone? Did I forget a topic? Because I was very close to forgetting the IVT yesterday. I do not think I'm forgetting anything, so let's begin without further ado. Okay. So the first topic is divisibility, and I'll just quickly mention the problems of divisibility. I won't be writing down things like A is equal to QB plus R gives a unique way to write A, and Q is called the quotient, R is called the remainder, whatever. I'm assuming that knowledge today, but I will mention some basic properties of division. So properties of divisibility. First, any number A always divides 0, and the number 1 always divides A, and A itself always divides A. Okay. If a number divides 1, then that is equivalent to saying that the number is either 1 or it is minus 1. There are no other divisors of 1. Fine. Say divides B and C divides D, then AC divides BD. If A divides B and then B divides C, then you can get rid of B and directly say that A divides C. If you have two numbers which divide each other, then they have the same mod. That is to say, A is equal to plus or minus B. Okay. And one last thing, if A divides B and B is not equal to 0, then the modulus of A is always going to be less than or equal to the modulus of B. So a number that is whose modulus is larger than another number cannot divide that number. Okay. Fine. Finally, if A divides B and A divides C, then A divides this linear combination AX plus BY for all X comma Y integers. Okay. There is someone in class who has joined as a number instead of a name. Can you please tell me your name? 6862623. Okay. No name. Fine. So that covers divisibility. That's all the basic properties. Then you have the greatest common thing, divisor. And I'm sure you know the definition. So I'll just mention the properties that are good to know. So given integers A and B, not both of which are 0. So only one is 0, but not both. Are 0. Then there exists, so then I should write the then as well, I guess. Then there exists X and Y integers such that the GCD of A and B is a linear combination of A and B. Okay. So what does this tell you? This immediately tells you that if you have two co-prime numbers, then there are some X and Y such that you can write AX plus BY is equal to 1. And this is a very useful thing to know. Okay. And another thing that is immediately obvious is that the set T of all ax plus by as x and y range over the integers is precisely the set of the multiples of the GCD. This is precisely n times the GCD. Okay. Should mention that as well. So if GCD is 1, I am mentioning this separately because this is very useful. Such that ax plus by is equal to 1. Great. Okay. Now, as most of you have already seen number theory, you know that you can play around with things that are inside the GCD as well. So one thing that you can do is write this. GCD of a comma b is actually equal to the GCD of a minus b comma b, where so there is some assumption to be made, a is greater than b, and let's say they are both positive as well. However, remember that you cannot add it. That's why I have to assume positive above. This may not always hold. Okay, so of course this one can be generalized a bit more. So you can get minus nb comma b here. So a further condition would be n belongs to positive integers, so natural numbers. Okay. Now what? A few more. So with number theory, the results are usually something that look obvious at an immediate glance. Of course, you don't really realize why these are such deep results in number theory. But as you hopefully grow older in the world of mathematics, you'll come to see why number theory is such a famous and important field. Okay, so if the GCD of two numbers is some quantity d, some number d, then the GCD of a divided by d, which is obviously an integer, so is b divided by d, is 1. So that is, this is coprime. Okay. Then you have what's called Euclid's lemma, but you don't really need the name. The result will still be obvious to you. So you know that this implies that this doesn't imply anything. I forgot one condition. And say the GCD of two of them is 1. So A and one of these, B and C is 1. Then immediately you realize that A must divide C then. Okay. Of course, if you don't enforce GCD AB is equal to 1, then you could have the case that A divides B times C, but it doesn't divide B or C individually. So an immediate example of this would be 6 dividing 4 into 3. So 6 doesn't divide 4, 6 doesn't divide 3, but 6 still divides 4 times 3. Okay. Okay. So then how do you find the GCD? Obviously, you know one method that you've learned in school long ago, but how do you do it when you have very, very big numbers? That's where the Euclidean algorithm comes into play. And this works because of one very particular lemma. So let me state the lemma, then I'll state the algorithm. The lemma is that if A can be written as Q times B plus R, then GCD of A times B is GCD of B times R. Okay. Now the algorithm itself. Now the algorithm. Let A and B be two integers whose GCD is to be found. So that's what we're trying to find. So you can assume without loss of generality that they are both non-negative and that A is greater than or equal to B. You can even assume they are both positive as a matter of fact. If it's zero, then you don't really need to find the GCD, do you? So step one, you write that A can be written as some Q1B plus R1, where of course 0 is less than or equal to R1, which is strictly less than B. Right. Now at this stage, so let me change colors. If you have that R1 is equal to 0, then you immediately see that this means B divides A, and therefore their GCD is B. Fine. If not, you proceed to step 2. So if not, you move on to step 2. And step 2 is divide B by R1 to get B is equal to some Q2 times R1 plus R2. Here the condition on R2 is of course this. And once again, if at this stage R2 is 0, we stop. If not, you keep repeating. Or do you keep repeating? So step 3 would have been divide R1 by R2 and write R1 is equal to Q3 R2 plus some R3 and so on till you get a 0 remainder. And as soon as you do, you immediately know. So why do you know that this division terminates, that this leads to a 0 remainder at some stage? So this terminates because this division process continues until some 0 remainder appears. Suppose at the n plus 1th step. So at the n plus 1th step, what would be the equation that you obtain? It would be something like R n minus 1 is equal to Q n plus 1 times Rn plus 0. So that is the equation you are looking for. Then at that stage, so let me write where Rn minus 1 is divided by Rn. And you are supposing that at this stage you get a 0 remainder. Then the last non-zero remainder, which is Rn, is equal to the GCD we were looking for. And I won't write this down, but you can see that this division always reaches a 0 remainder because the sequence B, R1, R2, and so on is decreasing. And it's a sequence of non-negative numbers. So it has to, of course, reach 0 after at most B steps, right? So say something. Why is chat so silent? Do you agree? Okay. So that's the division algorithm or the Euclidean algorithm. Let's look at one example just so this is absolutely clear. So say my problem is to find, so let's look at both ways. So let me look at a problem. So if I have a problem that says find x comma y belonging to the set of integers such that their GCD, the GCD of these two numbers is equal to this, which we know will happen as we've previously noted. Okay, so first I need to find the GCD, of course. So to do that, I start with step 1. And I write that 1, 2, 3, 7, 8 is equal to 4 times. So I have already done these calculations, of course. So that's why I can be so quick at this. I'm not a human calculator or anything. Step 2, you then write that 3054 is actually 18 times 162 plus 138. Step 3, you write that 162 is actually 1 times 138 plus 24. And it's good practice to always write the thing that you're going to divide in the next step in the bracket so you don't lose track. Step 4. Now 138 is 5 times 24 plus 18. Step 5. 24 is 1 times 18 plus 6. And at step 6, I will reach my zero remainder, which is 18 is 3 times 6 plus 0. So I look at the step above and the non-zero remainder there. So now I know what the GCD was. The GCD of 1, 2, 3, 7, 8 and 3054 is 6. Now I wanted to find x and y such that that linear combination was equal to GCD. So now we reverse engineer. Now you start by noticing that 6 is 24 minus 18. So I'm starting with this step and then I'm going to go the other way around, which implies that 6 is equal to 24 minus 138 minus 5 times 24, which is equal to 6 times 162 minus 138 minus 138, which means 6 times 162 minus 7 times 138. So you can see, right, what I'm trying to do. I'm trying to reverse engineer the 6 steps above to get 1, 2, 3, 7, 8 and 3054 back out. Right. You can find a more detailed explanation of all of this in Burton's book, which is where my example can also be found. I think, if I remember correctly. Then you have, so this is 132 times 162 minus 7 times 3054, which is equal to 132 times 12378 minus 4 times 3054 minus 7 times 3054. Now I know most of you are thinking this is so long and tedious. Maybe there is a shorter way. And the thing with algorithms is that they don't worry about being the fastest in one particular case. They worry about being the fastest on an average. So this leads to a good thing when you try to do it arbitrarily for any tool without any prior knowledge about them. Of course, there might be some value that you can easily find in some situations, in which case you do so. And minus 535 times 3054. Therefore, this works. Therefore, my x is 132 and y is minus 535 is one solution, which is all I cared about. Okay, not spending more time on this. Few more properties of the GCD. So if you have some natural number k, then the GCD of Ka and Kb is k times the GCD of A and B. Okay. Now, if you also know what the LCM means, then you also have this result. Perfect. So you can realize that this tells you that the LCM being equal to the product is equivalent to saying A and B are co-prime. That is, the GCD is 1. Okay. Now that covers these three things. Now we move on to Diophantine equations. Who are you? I don't know. Try refreshing. Try to make browser, I guess. Okay. Anyhow, Diophantine. The rest of you can hear me, right? Can someone else confirm? Yeah, that's not my issue. Then I don't have the time to spend on tech issues today. Okay, Diophantine equations. And we only need to worry about the linear situation. So the equation that we are concerned with is an equation of the form ax plus by is equal to c, where so we are limiting these solutions. So of course, immediately you know that this is a line, but we are only concerned with integer points, and even more so, just so that it remains interesting, a b not both 0. So maybe one of them is 0, in which case it's a simple equation to solve. But let's put that condition in. If both are 0, then this is obviously absurd, unless c is also 0. But the facts you need to know about this only have a solution. By solution here, I will always mean integer solution. When GCD of A and B divides C. Otherwise, there is no solution. And this follows immediately from our properties of the GCD, wherever I wrote them. Fine. And you would like to know how to find a solution as well. So to always be able to find, or rather to construct as many solutions as you want given one solution, you have this theorem. So ax plus by is equal to c has solutions x is equal to x naught plus b by d times t, and y is equal to y naught minus a over d times t, where x naught and y naught is some given solution. So by naught. And the d is just the GCD of a and b. So if you have one solution, you can cook up as many as you want. So for all t belonging to zero. So any value of t will output one more solution to the original Diophantine equation. Okay, that's that. And we will be revisiting this, but I'll put a tick mark here regardless. For now, let's move on to something I forgot to mention in my sketch: prime numbers, the building blocks of all the natural numbers. So I'm sure all of you know what a prime is. Anything greater than 1 which is not prime is composite, and you know some basic results like p divides ab implies that p divides a or p divides b. Why is this? Because here you cannot have a situation like 6 dividing 4 times 3, because if it were prime you won't be able to split its divisor into the two terms on the right. They'll have to occur together, right? Okay, this can be generalized as a matter of fact, obviously, to say something like this: ai for some ai. Okay, and a particular situation arises when you have something of this form, where p and all the qi's are prime. Then this means p is equal to qi for some I, because a prime dividing another prime means they are equal, right? Okay, now we have the big result, the first big result, the fundamental theorem of arithmetic. And maybe I'm going to horribly misspell arithmetic, but I think this is correct. So what this states is that every natural number n can be expressed as a product of powers of primes, can be expressed as a product of powers of, say, distinct primes. And the important thing, so this is all good, the important thing is that this expansion or this representation of n is unique. Of course, you are allowed to write the primes in whichever order you like. Which the factors occur. Okay. So in general, the way it is and keep that in mind. This is a unique way of expressing n. Okay. Let's take a short detour and look at a rather uh, elegant proof of the fact that there are infinitely many primes. This was Euclid's original proof. Of course, there are plenty of more ways to prove this fact now. So what Euclid argued was that suppose there are finitely many primes. So if there are finitely many, you can easily list them down. So say these are all the primes in the world. Then consider the number n is equal to, capital N is equal to 1 plus the product of all your primes. Okay. Then there are two cases. Case 1 would be n is prime. So of course any number greater than 1 is either prime or composite. Suppose n is prime. Then my list of primes is clearly incomplete, because I have constructed a prime not on my list. Or slightly less trivially, you have case 2. N is composite. Then there must be some factorization of n in terms of primes according to the fundamental theorem. However, none of my PIs will divide n. So none of my primes divide n, which means the prime factors of n are somewhere other than my list. Which means there are some primes not on my list. So once again, my list is incomplete. And since this argument can be repeated as many times as I'd like, this implies that the list of primes has to be infinite, of infinitely many elements. Okay. Now, one more important, so let's call it a problem and immediate solution, I guess. So you can think of it as a result, but it's pretty easy to prove immediately. So given an integer n, or rather natural number n, let's say n greater than 0, there are always n consecutive integers, all of which are composite. So in other words, I can always find two primes which have n numbers between them, n composite numbers between them. Okay. All of which are composite. And the way you prove it is that you just give a list of n numbers which satisfy this. So you consider these numbers. So this is not prime because it is divisible by 2. So it is composite. This is divisible by 3 and so on. This is divisible by n plus 1 itself. And these are n numbers, so you are done. Right? You go so far with me? Any doubts? No doubts? Are you even with me? Or have all of you slept? Okay. There exists infinitely many primes of the form dn plus 1, where d is a fixed integer. Okay, I don't know that. I'm not going to take your word for it either. If you have a proof, I'll take that. But that's not a result we need to know. I think this is slightly more advanced, so that is what my gut tells me. So there is something called, so this is off topic and you don't need to know this for entrance, but there's something called Dirichlet's theorem, which says that given two coprime numbers A and B, the AP, A comma I plus B comma I plus 2B and so on, contains infinitely many primes. So I think this should follow from one such sequence. Because D and 1 will be coprime. So you can treat 1 as A and D as B, and then immediately follows. But to prove Dirichlet's theorem, you need a lot of fancy machinery. Okay, let's not go there. Instead, let me put a tick mark here and move on to congruence. Once again, we are only concerned with the linear curve. So let n be a fixed integer, or rather natural number. Then n divides a minus b can be written as a is congruent to b modulo n. Okay, so this is what this symbol is read as. A is congruent to b modulo n. Okay. Then the set 0 to n minus 1, that is all possible good quality remainders, is called the set of least positive residues modulo n mod. Okay. So why is this notation something we are concerned with? Because this makes doing a lot of things easier to look at, mostly. Let's look at some properties. A is congruent to B mod n is equivalent to saying A and B leaves the same non-negative remainder when divided by n. Okay. Now, what are some good properties that are not immediately obvious? A is always congruent to itself. And this is an equivalence relation as a matter of fact. So this is reflexive. It is also symmetric. So if A is congruent to B, then B is also congruent to A. And it is also transitive. So if A is congruent to B, mod n, and B is congruent to C, mod n, then A is congruent to C, mod n. Some people don't write the mod n brackets. I'm just used to it, so I do it. But you can omit the brackets around mod n if you'd like to. Okay. Now the properties that actually make it useful. If A is congruent to B, mod n, and C is congruent to D, mod n, or that they are modulo the same thing, then you can add. Then you can add them on the corresponding sides. And you can also multiply them on their corresponding sides. Can you do it on the other side? So can I say that AD is congruent to BC? Yes, I can, because I know that I can just flip my congruences. It doesn't matter, right? Okay. Then you can add the same thing to both sides without changing the congruence. So if A is congruent to B mod n, then you can add any C to both sides, or multiply a C on both sides. Right. And you can also raise powers on both sides. You can raise both things to the same positive power, not a negative power, because then of course it will become absurd. Because it would be 1 over something. We are only concerned with integers right now. Okay. Now you have this is not related. Right. This is an important result. So you can try to prove this one as well. If A is congruent to B, mod n, then the GCD of A and n is actually the same as the GCD of B and n. Great. Okay. So now, this is something I forgot, but thankfully it's here in notes as well. So special tests of divisibility, and I'm sure you know all of these already. So divisible by 2, you can test it by looking at the last digit is even, so it is 0, 2, 4, 6, or 8. In that case, the whole number is divisible by 2, divisible by 3. So I'm only stating the ones that are common practice and are useful to know and are too difficult to use. I know there are some weird divisibility tests for 7 as well, but I don't care. Divisible by 3, so divisible by 3. Divisible by 5 would mean last digit is either 0 or 5. Then you also have divisible by 9, which is sum of digits. If x square is congruent to 1 mod p, can we always say that x is congruent to plus or minus 1? No, you cannot. I don't think so, no. So take 3. Okay, is p a prime? If p is a prime, then my counter example that immediately came to my head won't work. Maybe another one would. But is p a prime? And one final one is 11. If p is not a prime, then look at 3 and look at mod 8. So 3 square is 9, which is congruent to 1 mod 8, but 3 itself is congruent to plane root 3. Okay, p is prime. In that case, can n square minus 1 ever be a prime? So your claim is that x square minus 1 is some prime multiplied by some constant, so x minus 1 x plus 1. Okay. Oh, okay. So maybe I'll just type. So that's what you should question. Depending on that, you can put it further. But anyhow, divisibility by 11. For this, you check the alternating sum. By alternating, I mean the second one, add the third one, subtract the fourth one, so on. Alternating sum of digits is divisible by 11. So these are the 5 you need to know, which are common practice. Now coming back to linear congruence. So let's look for solutions to the equation. We want to find x belonging to z such that ax is congruent to b mod n. So of course a, b, and n are natural numbers. But then you realize that this is the same as saying that ax minus b is divisible by n, which is the same as saying ax minus b is some ny, which is the same as saying ax minus ny is equal to b, which is the same as saying ax plus my is equal to b. At this stage, m is minus a, which is a Diophantine equation, which we already know how to talk about. So let's forget about this step and let's just work with minus and y instead. Easier. to work with. So when does this have a solution? So this has solutions only when anyone? Okay, only when GCD of A comma N divides B. And as a matter of fact, since we are now concerned with congruence, solving the congruence instead of the Diophantine equation directly, if this happens, so if it does admit solutions, it has so many, so GCD A comma N, that value mutually congruent or rather incongruent solutions. So any other solutions will actually boil down to one of these solutions mod n. That's what this means. Okay. So now instead of looking for just solutions, I'm looking for solutions mod n. That's the interesting thing for me now. So if they are co-prime, A and N are co-prime, then this linear equation, linear congruence, has one unique solution, mod n. Okay. Now let's look at another big name result. That is the Chinese remainder theorem. Okay. So this states that let n1 to nr be natural numbers be co-prime natural numbers, pairwise co-prime rather, so such that their GCD is always 1, take any 2. In that case, then the system of linear congruences so this is my system. I have some x which I'll be looking to find. Is congruent to A1 mod n1, is congruent to A2 mod n2, and so on till my nr, some kr mod nr. This has a solution, and that solution is actually unique in some regard. Has a solution, has a simultaneous solution. And this is unique mod 1 into nr. So this is a product. Okay. But what's more interesting is the proof of this result. Let's look at the proof, because the proof will actually be construction of this solution. I did not give a counter example. I gave a counter example in the situation where P is not prime. If P is a prime, I will have to think a bit. and we don't have time to waste today, unfortunately. So if maybe we have time after finishing all of this, I'll think about it a bit more. But right now, I need to get through this first. Okay. We are done with linear congruence. We are at CRT, so it's a part of this. That's what we're doing. We have a few more topics left after this. Okay. Now let's look at a proof of this thing. So I will make things easier for myself by calling n this product, and for each k is equal to 1 to r, let capital N subscript k be small n. This thing. So that is, you remove nk from the product. That's it. Now, since GCD of capital NK comma small nk is always 1, this solution always has, this congruence always has a solution. So this congruence is which talking about clearly, nkx congruent to 1 mod nk for all k has a solution. Say one such solution is xk. Okay. Now you look at this number, which will be your solution to the simultaneous equation you were worried about in the first place. A1 n1 x1 a2 into x2 and so on till ar nr sar. Then since ni is congruent to 0 mod nk for all I not equal to k, I can say that x bar is always congruent to ak nk xk mod nk, because the rest will reduce to 0. Okay, but we chose rxk such that nk times xk is congruent to 1 mod nk, which means that x bar must be congruent to ak mod nk. Think about why this is true for a bit if you would like to. So therefore, x mod is a solution. You can prove uniqueness yourself. It's homework because I have more results to go through. Okay. Now another famous result is Fermat's little theorem. And this states that if P is a prime and you have some A such that P doesn't divide A, then this congruence is true. An immediate corollary is that if you get rid of the condition of p not dividing a, then you have the slightly modified statement that looks like this. And remember that the converse is not true. That is, this cannot be used as a test for prime numbers. So if you have such a congruence, that doesn't mean that p minus 1, the power is a prime minus 1. Okay, why is the converse not true? It is not true because of a result. You can look at, but you don't need to know really. So if p and q are distinct primes, such that a to the power p is congruent to a mod q, and a to the power q is congruent to a mod p, and a to the power pq is congruent to a mod pq. Our pq is clearly not prime, so you see why this doesn't work in the converse. Fine. Another famous result is Wilson's theorem. This can be used to test for primes, as we will see. This states that if p is a prime, then p minus 1 factorial is congruent to minus 1 mod p, or equivalently, p divides p minus 1 factorial plus 1. Converse is also true. So if such a situation arises, then p has to be prime. Okay, that covers these. So now just the number theoretic functions left to look at. So there are three that we'll be looking at. So let's look at two first, and then we'll come to the third. Maybe we'll look at some other results in the meanwhile, and then come to the third. Okay. So the three that will be, so let's look at two first. These two will form a more important case. Great. I have no idea what that is, so I answer no. Okay, so tau of n will denote number of positive divisors of n. And sigma of n will denote sum positive divisors of n. We'll later look at phi. Let's come to that. So if n can be factorized like so, here kr, then tau of n is equal to k1 plus 1 k2 plus 1 and so on till kr plus 1 is equal to, in a more compact form, you can write this like so, not pi k. And of course, you can prove this combinatorically. It's a straightforward proof. So any prime divisor will, not prime, any divisor of n will be made out of these pi and some power of those. So you only have k1 plus 1 choices for a power of p1 and k2 plus 1 choices for a power of p2 and so forth. You have k1 plus 1 because you can also have the 0 power. That is, you don't have a pi term. So that's how this follows. Then you have sigma n, which has a slightly uglier form. Looks like this. And you can try to prove this yourself. It's also a more or less straightforward proof. If you want this in a compact form as well. Okay. Now, before I move on to phi n, let me say some more things in a more broader sense. So a number theoretic function, by a number theoretic function, I mean a function from z to z. So a function, a number theoretic function or a function f from z to z is called multiplicative if fmn is equal to fn, but this only needs to hold when mn are such that their GCD is 1 for all co-prime mn. Okay. Your functions tau and sigma are multiplicative. So this is a property you can use to find these easily in some situations. Okay. Then you have smart needed. Okay, there is then this I'll discuss in the end. So let's come to Euler's phi function then. I waste time. Also called the Toshin function. I have no idea where that word comes from. So now phi n is described to be the number of positive integers less than or equal to n, which are relatively prime to n itself. Okay. Now let's build up to a general solution of a general formula for phi n. So the first case is when p is a simple prime. So you can find this combinatorically and using the fact that phi can be proven to be multiplicative. Some of these follow immediately from just combinatorics. In the end, you will need a bit of multiplicity. If p is prime and k is some natural number, then phi of p to the power k is p to the power k minus p to the power k minus 1, or in a more handy form is this. Okay, you also know that phi is multiplicative, and then you can immediately give a general formula. If n is p1 k1 blah 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 pr kr, then phi of n is equal to n times 1 minus 1 over p1, 1 minus 1 over p2, and so on. In a more compact form, it's this thing. Okay, so now what does this formula tell you? This formula tells you that for all n greater than 2, phi n is even. And now you have a generalization of Fermat's little theorem as well. So a theorem. So if you have a natural number n and some a such that GCD of a and n is 1, and then a to the power phi of n is congruent to 1 mod n. And this is not really a result you need to know, but it's a curious one, and Gauss proved this as well. So for all n greater than 1 natural number, of course, n is actually the summation of phi d over all the divisors of itself. Okay, and we don't have a lot of time, so maybe I'll just mention this one more curious result that you don't really need to know. For n greater than 1, we can say that this summation so that is the summation of all natural numbers less than or equal to n which are co-prime to n is equal to half n phi n. Maybe you can try to prove this. And there ends the number theory review. Are there any questions? Quickly, please, because as I've previously mentioned, I need to take another class immediately afterwards. Are there any questions? No? Okay then. Where ends the number theory review? Okay, someone is typing. I'll wait. Ah, yes. So can square ever be? So I'm not sure that np minus 1 is over of 9. Yes. Because np minus 1 over of 9. So okay, I've saved the board. Maybe I can do some scratch work. Okay, so the class has ended. You are free to leave. And let's